I'm sure all of us remember that first day at a new job, or maybe a new school, or maybe moving to a new city and driving around there for the first time. Even though you had a lot of skills and everything, you still were, let's say, not ideal for the job or for the new city or anything like that. You just weren't at your best. You were a day one employee or a day one driver. The problem with generative and predictive AI, including large language models, as I have pointed out many times, is that they basically act like day one employees or day one drivers every single day. But Google Research, creators of the original Transformer, might have a solution to this problem, and if it works, it will be a Titanic game changer. Let's take a look. Hey y'all, it's Dr. Know-It-All. I am really excited about this paper. I actually did not have time to actually do this video. I'm shooting it late at night so I can squeeze it in amongst other busy things that are going on at this time of year. But I was really intrigued by this paper, and it potentially will solve a huge problem that I have talked about over and over and over again on this channel, which I call localized memory, which is basically memory that's not generic. Memory that's associated with, let's say, you and your own personal experiences, as opposed to the generic experience of every human being. And as you might have noticed, I snuck in the word Titanic into the intro because the title of the paper is Titans Learning to Memorize at Test Time. So this is a very big deal, and weirdly coincidentally, today as I was working on this paper, I saw Matthew Berman's excellent video on Sakana AI's take on resolving the localized memory problem as well. If you haven't seen my video on Sakana AI's AI researcher, definitely check that out. I will leave a link up there and at the end of this video. So anyway, almost definitely I will review that paper as well, because I want to see how the two work. From Matthew's video, it sounds like these two actually might be able to work together. You might be able to use both of these things in harmony with each other. They're not necessarily competing products. They might be complementary, and that would be really, really cool. So returning to the introduction, I'm going to use the dual case studies of working for the first day at a new job and driving for the first time in a new city. And I think both of these are excellent case studies and will help us to understand this paper better. By the way, I always give shout outs when I think papers are written particularly well. This one is not. This needs to be proofread. It needs to be reconstructed. There's a lot of really important and very, very cool stuff that's buried in the middle of the paper. It could be done better, guys. I would honestly volunteer to help to rewrite it and get the grammar correct, because it seems like some of this is just English as a second language sort of issues, but also there are organizational issues and things that could be done better as well. So anyway, the upshot is the paper is more difficult to understand than it could be, but I think that these two examples are going to help us to kind of navigate this paper and understand. So what do you get as a first day employee, or for those who might be very young, people who are going to a new school for the first time, but I'll just say a first day employee. So let's say you've gone to high school, you've gone to college, you've got the mad skills, you know exactly what you're going to do, you're a data analyst, whatever your job is or something. You have the generic knowledge, you know how to do something, but you have never worked for this company before. You don't know the other employees, you don't know the way that they work, you don't know the company procedures, you don't know the handbook yet. There's all these things that you have to, bone up on. And over the first weeks and months, you will get better and better as an employee because you'll learn this localized knowledge. You'll understand what's going on in this context and what you need to do in this context in order to succeed. Same thing is very much true of driving. If you drive in a new city, the first couple of days, you don't know where you're going exactly. I mean, you have the driving skills, right? Let's say you've been driving for 10 years. You're a perfectly good driver, but you don't know all the little local tricks. You don't know what lane to be in at what particular point. You don't know about the traffic patterns exactly and how aggressive or not aggressive other drivers are. You don't know the secret routes to get around traffic jams. All of that stuff makes you a poorer driver than a city that you've lived in for a couple of years. You're going to be like really good at driving in that city. And again, you've probably heard me talk ad nauseum about the fact that Teslas drive like generically good drivers. It's like the first time they've ever been in a city every single time you drive. Very, very frustrating. So why can't deep neural networks, and in particular transformer-based architectures like large language models and Tesla's full self-driving, why can't they just overcome this problem? Well, the issue is basically memory. Effectively, large language models, full self-driving, etc., they have a short-term memory. They know things that are going on right now, and they also have a task-related persistent memory. In other words, if you're a data analyst that's been trained, you've taken classes on that, and you know that generic information. And for full self-driving, it's like, how do you drive? How do you steer? How do you avoid collisions? All of that kind of stuff. That's like the basic sort of groundwork that you need. And then, of course, the short-term memory is, what am I doing doing right now, if I'm driving, how do I not crash? If I'm a large language model, an agent that's working for a company or something, it's like, how do I accomplish this specific task that they've asked me to do? But what's missing in between these two is a long-term memory that can be adjusted over time for localized conditions. So with that in mind, let's go ahead and read the entire abstract. I'm going to read the abstract in its entirety, but then I'm going to skip through the rest of it because it is a very long paper. And so, we don't have 3 hours for me to talk about it. So I'll try to just hit the highlights, the important stuff, but not gloss over how they do this because I think it's very important. Anyway, over more than a decade, there has been an extensive research effort of how to effectively utilize recurrent models and attentions. So that would be recurrent neural networks, RNNs, and attentions would be transformers, things like that. While recurrent models aim to compress the data into a fixed size memory called the hidden state, attention allows attending to the entire context window, capturing the direct dependencies of all tokens. That's, again, that sort of short-term memory where it has a sliding window over some sort of context. This more accurate modeling of dependencies in transformers, however, comes with a quadratic cost. What that is x squared. So if you double the length of the prompt or whatever it's having to interact with, you quadruple the amount of, compute that it takes, right? 2x goes to 4x because it's x squared. And if you 8x it, then suddenly you're looking at 64x the compute power that's needed. So going up quadratically is a bad thing. It's better than x cubed, but it's certainly much, much worse than x to the first power, where it just goes up linearly. Anyway, this quadratic cost limits the model to a fixed length context. In other words, you take a window and you slide it over the text for the case of a large language model, or you slide it over the last 10 or 15 seconds of driving for a full self-driving model, and you forget about all the stuff that happened immediately before that, and that is a significant problem because you're forgetting. It's a forgetting problem. So to overcome this, they say, we present a new neural long-term memory module that learns to memorize historical context and helps an attention to attend to the current context while utilizing long past information, in other words, long-term memory. We show that this neural memory has the advantage of a fast parallelizable training while maintaining a fast inference. Parallelizable training is super, super important. In other words, it's not just a toy project they're working on here. If you can parallelize the training, in other words, you can do it on many, many GPUs at the same time, then you can do inference, you can do test time kind of compute really, really fast. You don't have to do things in order. That was one of the problems with recurrent neural networks, for example, was they were entirely linear. They couldn't parallelize. And that was a huge shortcoming in RNNs. So it's super good to see here that they've been thinking about this. And of course, given the fact that it's Google research and they want to productize these things, parallelizable is very, very important. But anyway, from a memory perspective, we argue that attention, due to its limited context but accurate dependency modeling, performs as a short-term memory, what I was just saying, while neural memory, due to its ability to memorize the data, acts as a long-term, more persistent memory. And that's an important, thing that you have to have. You have to have these two things working in harmony, and then there's a third actually too. Based on these two modules, we introduce a new family of architectures called Titans, and they don't really explain why they call it Titans. I think it's a cool name, but I wish I understood a little better why they call it that. Anyway, and present 3 variants to address how one can effectively incorporate memory into this architecture. Our experimental results on language modeling, common sense reasoning, genomics, and time series tasks show that Titans are more effective than transformers and recent modern linear recurrent models. They further can effectively scale to larger than 2 million context window size, 2 million tokens, with higher accuracy in needle in a haystack tests compared to baselines. So now we're going to move on to the meat of things. I'm actually not going to look very much at the tests because I think that we'll understand the import of this without going through the tests. But the end of the paper, they go through, tables and tables and all this kind of stuff, examining how they do better than everybody else. But we'll just take that for granted at this point. What I want to do instead is look more carefully at how they solve this memory problem. So first they talk about transformers, how they store key value associations and retrieve them by computing pairwise similarity between queries and keys. So this is the classic QKV in transformers. If you haven't seen my video on transformers, definitely watch that. I'll put that at the end of the video, and I think I'll put them in the description as well, so you can watch those at your leisure, because I think those is, it's important to understand. I don't really have time to explain transformers here. That's just too deep to go into, but I did another video that gets into that, so definitely watch that one. So as they continue on here, accordingly, by design, the output of a transformer is exclusively conditioned on the direct dependencies of tokens in the current context window. Tokens you might think of as words, but they also, they talk about video and stuff like that. You might think, why do you care about having more than 2 million tokens? When are you ever going to have 2 million words in something? Well, think about a video, or think about thousands of books as opposed to one book or something. It's very, very easy to go over 2 million tokens. And so you need some sort of way of attending to the important parts of memory and also storing away important parts of memory, right? You have to continue to learn. The big problem with transformer models like ChatGPT, etc., is that you train them. It's a very expensive process to train them. It costs potentially hundreds of millions of dollars to train them. And then you just push them out and they're first day, right? It's like the movie Memento. I'm a huge fan of Christopher Nolan's early stuff. In fact, all of his movies. But anyway, it's an excellent movie if you haven't seen it. But it's this idea of you've got this guy who just, every time he wakes up, he can't remember anything. And so he has to give himself clues. Those clues, by the way, would be sort of like retrieval augmented generation, which I'm sure you've heard about, RAG. That would be, if you were the new employee, it'd be like somebody hands you the handbook and you can look up what you're supposed to do. So it kind of works, right? I mean, it's going to make you better than an employee without any references at all, but you're still going to be a first day employee who's just leafing through the book every time you have to figure out how to do something. It's going to make you better, but not great. So anyway, we want to get around this quadratic complexity issue. We want to reduce that. We want to be able to learn things as we're doing things and then stuff them away into long-term memory, but only the parts that actually matter, because we don't have an infinite context window, just like we humans. We only have so much room in our brains to store information. So we have to decide, this is important, this isn't important, and I'm going to remember the thing that's important, and I'm going to throw away the stuff that's not important, which is 99% of your life. And from that, we actually build not just the skills we need generically, but the specific skills we need to do the specific jobs, the specific driving, whatever kinds of tasks you have to do. Those are the things that you're going to remember and get better and better at. And that's what we need large language models to do. And that's exactly what Titans purports to do. So note that they say up here, we need the ability to actively learn from data and memorize the abstraction of past history. That's the important part. Then they talk a little bit about memory, a perspective on memory. They say memory is a fundamental mental process for us humans and is an inseparable component of human learning for sure. Then continuing on, they say transformers can be seen as architectures with growing memory in two similar steps. That is, the pair of key and value matrices acts as the model's memory, and the model 1 updates the memory by appending the key and value to the memory without compression. This is important. It just remembers everything. It's short-term memory. It's basically just taking it all in. And 2, retrieves query vectors corresponding memory by finding the similarity of query and key vectors, which is then used to weight the value vectors for the output. In other words, it figures out the probability of the next word for a large language model or something like that. Then we get to a key part of the paper here. Revisiting our understanding of human memory, it is neither a unitary process, in other words, it's not just one thing, it's multiple things, nor does it serve a single function. There's a writing problem, just a small one that needs to be rewritten. In fact, memory is a confederation of systems, for example, short-term working and long-term memory, each serving a different function with different neural structures. They say they're designing a long-term neural memory module that can efficiently and effectively learn to memorize at test time. That's the important part. That's how you get localized knowledge. Remember that you're training this thing, a very, very expensive model, can't do that on your home computer or your car or something like that. But what you can do is you can learn at test time and you can redo the weights of your model a little bit to adjust for this localized knowledge. And the important part is you can do it at test time. You can do it when you're actually doing the task rather than having to send the data all back to the mothership and do a full retraining run. This is critically, critically important. So then we get into the architecture called neural memory, and then Titans is sort of the expression of this neural memory module. Anyway, we present a deep neural long-term memory that as a meta in-context model, and interestingly enough, that was exactly how I said that Tesla should solve their full self-driving memory problem, was a meta model that actually learned the model itself. So I had the idea, of course, having an idea is whatever. But anyway, these guys, they've acted upon that. They're creating a meta model. And as we'll see, the loss function is actually the other model, the one that it's learning from. So it's very, very cool. Anyway, it learns how to memorize/store the data into its parameters at test time. So that again is the critical thing. It's learning at test time. It's not having to go back and be retrained. Anyway, as they say, inspired by human long-term memory systems, we designed this memory module so an event that violates the expectation being surprising is more memorable. So this is really exceptional. This is a very key insight into how to transfer current, short-term memory into long-term memory. Use surprise as your metric. What does surprise mean for us humans? It means, like, if I open up my front door and my wife is standing right there in front of me, right? I open it up and I see her and she's right there and I'm like, ooh, that's mildly surprising, right? I'm like, oh, I was not expecting you to be there. It's a little bit surprising. She might be surprised too to have me suddenly open the door and just, be standing there or something. So that's a little bit surprising and I might remember that for a day or two. But what if I opened the door instead and there was a large bear standing there holding a cherry red Tesla Roadster model? If I opened the door and saw that, I would remember that for the rest of my life. That would be incredibly surprising. And so what the authors of this paper have done is they've said, this is the moment when we need to transfer short-term memory to long-term memory. When something is surprising, and the more surprising it is, the more effect it has on long-term memory. If it's just a little bit surprising, it's like, okay, maybe put it in there, but no big deal. But if it's super surprising, you put it in there and it's like, yeah, stick around, buddy, because this was something very unexpected. It violated what I thought was going to happen, and it's worth remembering for that reason. So how do you do this mathematically in a large language model? Well, it's actually pretty elegant. To this end, we measure the surprise of an input with the gradient of the neural network with respect to the input in associative memory loss. And then they talk about memory decay. But first, let's take a moment and think about what's going on here. So their way of measuring surprise is the predicted outcome versus the actual outcome or something. So let's say that we had a series of pictures that were not quite random of dogs and cats. So maybe it was like one picture of a cat, two pictures of a dog, one picture of a cat, three pictures of a dog, one picture of a cat, four pictures of a dog. Something along those lines, right? You give the neural network millions of runs at this and it learns. It's like, okay, so I'm going to have, one picture of a cat, then n pictures of a dog, and then it will go back to being a cat again or something like that. If you give it that, it's going to learn that pattern. It's going to figure that out eventually, and then it will be able to predict what is the next card that I'm going to flip over. If you do it fairly early in the process and it's like one picture of a cat and it expects two pictures of a dog, so it's one picture of a cat, you flip it, one picture of a dog, it's going to be a dog next, and you flip the picture and it's a cat, let's say that's mildly surprising. It thought it was going to be a 55% chance that it was a dog and a 45% chance it was a cat. Yeah, no big deal, right? It's still learning the process. It's early in the process, not that confident of what it's going to get. But if you train this thing over and over and over again, and let's say it gets to the point where it's like 99.9% probability it's going to be a dog on the next flip and it sees a cat, that's highly surprising. For the neural network, the probability that it projected of what was going to happen versus what actually happened is massive. You've got a huge difference, and that registers very, very large surprise as opposed to mild surprise. So the larger the surprise, the more important it is, to stick into long-term memory. And it's pretty cool because you could think about that analogously to humans. I don't know that that's always the way we learn, but certainly surprise has an important impact on us remembering things. You tend to remember surprising things, and they aren't even necessarily surprising in a good way. It could be surprising in a very tragic way or something, right? The surprise of a car accident or something and you break your leg. You're going to remember that event for a very long time. So this is all very, very cool how it actually does that. There's another piece to this puzzle, however. It's like you only have so much memory, right? You have this box that you can put your memories in. So you have to throw stuff away. Something has to go away as you put new things in there. So they also present a decaying mechanism that considers the proportion of memory size and the amount of data surprise, resulting in better memory management. So in other words, it decays the memory. Things that aren't as important, it starts to throw them into the bin of history and you forget. Just like we as people do. You can probably remember what you had for dinner last night. Can you remember what you had for dinner 1 year ago today? Unless it was like a special day like your birthday or something, in which case it was kind of like a surprise. By the way, please subscribe to my channel. It's almost my 60th birthday. I would love to have you subscribe as a birthday present. But anyway, if it was a big deal meal, you might remember where you went, what you had to eat, etc. But if it was just a normal meal, there's almost no chance you're going to remember what you ate a year ago. So that in humans is that memory decay thing. It's throwing away stuff that's not particularly important to our lives anymore. And so then they say, interestingly, we find that this mechanism is equivalent to optimizing a meta neural network with mini batch gradient descent, momentum, and weight decay. In other words, there's an antecedent to doing this in kind of classical deep neural network literature at this point. And then they talk about the Titan's architecture. How do you effectively and efficiently incorporate memory into a deep learning architecture? We present Titans, a family of deep models that consists of 3 hyperheads. Number 1 is core. This module consists of the short-term memory. This is basically the transformers that we all know and love already in an LLM. Or in the case of full self-driving, it's the navigation. It's getting you from point A to point B, that short-term kind of activity that's going on. Anyway, it's responsible for the main flow of processing the data. We use attention with limited window size, right? So this is the stuff we're already familiar with. Then we have number 2, long-term memory. This branch is our neural long-term memory module that is responsible for storing and remembering the long past. This is the thing, you take your short-term memory, you put it in the long-term memory. The long-term memory sticks around. Not nearly as accurate as your short-term memory because you're having to always manage that memory space. You're having to throw things away. So it's not going to be as accurate, but it will help you to guide you, right? If you're driving around in a city that you're very, very used to, even though you can't remember every single time you drove this particular path, it doesn't matter because you've got the basic thing ingrained in your head. You kind of know the path you're supposed to go on, you know the traffic, you know the lanes you're supposed to be in, all of that kind of stuff is there for you in your long-term memory. And then interestingly enough, they also include persistent memory, which I wouldn't have thought about, but this is actually key. This is a set of learnable but date-independent parameters that encodes the knowledge about a task. In other words, how do you drive? This is the kind of thing that you can send off and spend $100 million training the large language model or your full self-driving model or whatever. You teach it how to drive. That part is date-independent. It can kind of remain fixed, and so you can train and you can keep this. You don't have to change this, which means you don't have to spend a ton of money retraining this thing. Think about a human being as an analogy, right? As we grow up, like maybe math, that's a skill that you might need in your job later in life. You've spent a lot of time, a lot of years, a lot of money effectively, whether it was the government or you or whoever was paying a lot of money to learn these skills. That stuff is important and you don't want to have to go and relearn it every single time. That would be very, very expensive. So that is your persistent memory. And that's a really cool insight that we have that as well, a skill-based memory. And so then they say that they present 3 variants of the Titans in which they incorporate memory as a context, a layer, and a gated branch. And of course, we will look at that in more detail. Alrighty, in the interest of time, we have to move forward a little more quickly now. Anyway, they say we present a neural long-term memory module, which is a meta model that learns to memorize at test time. So again, that's the important part. It's a meta model. It's a model on top of other models, and it learns at test time. And interestingly enough, I don't think it uses back propagation. It actually sounds like it only learns through forward propagation, which is intriguing. I don't know exactly how they do this. They say they're going to open source this code eventually, but they have not at this point. So I can't look at the code, but this is really interesting. That's one part of this paper I really don't understand is how it learns doing forward propagation only. But anyway, hopefully somebody smarter than me can explain that one. So first they talk about memorization and training. They say memorization has almost always been known as an undesirable phenomenon in neural networks as it limits the model's generalization. In other words, you can't just throw a bunch of text at it and it just memorizes the entire thing. That overfits to the problem. It doesn't allow you to generalize. In other words, if it just memorized the entire works of William Shakespeare and you could say page 37 of Julius Caesar and it could rattle off that page, well, that's cool. That's memorized, right? But if you said, write me a sonnet or write me a play in the style of Shakespeare, it would have no idea how to do that. It doesn't know how to generalize. It only knows how to regurgitate what it memorized. It's like bad learning procedures for humans again. It's like memorization is a very, very basic level thing. You want to get beyond that. You want to be able to generalize and utilize the information you have in creative ways, not just regurgitating what you've heard exactly. So with that in mind, they say we need an online meta model that learns how to memorize/forget the data at test time. And then they get into the learning process and the surprise metric. The key, as they say, to training long-term memory is to treat its training as an online learning problem in which we aim to compress the past information, x1, x2, xt-1, in other words, the things that happened in the past, into the parameters of our long-term neural memory module, M sub t. As we discussed earlier, an event that violates expectations, in other words, surprising, is more memorable for humans. Inspired by this, a simple definition of surprise for a model can be its gradient with respect respect to the input, which we also just talked about. And they mathematically formalize this in terms of surprise here. So this is how much does it differ from my expectations? I predicted A and I got B. But if it was a very, very close thing and there was a very low probability that A versus B, not very surprising. If it was a very, very high gradient between those two, big difference, then it's much more surprising, much more important to think about, to pay attention to. But then they have another key insight, which is that you can't just look at the surprise. You have to look at the things that happen after the surprise, right? So you have to look at past surprise as well as the momentary surprise. So in other words, you're surprised by something. It's like everyone goes like, surprise birthday party, right? You're walking the door and it's like, surprise. That's like right now. You just got surprised and then the surprise goes away and you have a party and stuff, right? That doesn't really matter that much, but if it's surprising and there's consequences to your life and you're like, ooh, I need to learn from this. I'm not saying consciously, but internally, you know, inside of your being, it's like, I need to learn from this experience. This was a bad experience. This should not have happened. So you're going to pay attention, not to just to right now, but to things that happen afterwards with a decay rate, right? You're not going to pay attention to this for weeks or months. It may be just a few minutes or a few hours that you pay special attention to it and actually learn in particular. And so that incorporates past surprise, and it's mitigated by this eta sub t. In other words, that's a decay rate. How small is eta versus how big is eta is how fast it's going to disappear. And then, of course, we have negative theta sub t, which multiplies by the momentary surprise of like how big of a surprise is this. So these two factors change the amount of attention that we're going to give to putting this into long-term memory. And interestingly, theta sub t is based on the surprise that you get based on what you thought you were going to get, whereas eta sub t is actually based on in context. It's like, okay, I'm going to look at the context and see how long I need to remember things. So it's a dynamic thing. It's not a constant. It's very, very cool. So as they say here, accordingly, a data-dependent eta can control if memory needs to, 1, ignore the last surprise by setting eta sub t to 0, possibly due to the change of context. In other words, you've moved on to something else, so it's no longer surprising. Or 2, fully incorporate the last surprise by setting eta sub t to 1, possibly as the token is highly relevant to its recent past tokens. So that's a very surprising situation that's continuing on, and I need to keep learning from that situation. And then they note that our memory module is a meta model, again, it's learning about learning, that learns a function based on the loss function. So it's learning based on the loss function of the other model. So in a sense, it's analogous to mathematically taking the derivative of something. So now we've got a way of putting short-term memory into long-term memory. We need the opposite of that, which is forgetting stuff that's not important anymore out of long-term memory. So when dealing with very large sequences, e.g. millions of tokens, so lots of books, entire movies, long-term driving around in a city or something like that, it is crucial to manage which past information should be forgotten, even with a very deep or very large matrix value memory. To this end, we use an adaptive forgetting mechanism that allows the memory to forget the information that's not needed anymore, resulting in better managing the memory's limited capacity. And so to do this, they use another variable, alpha sub t, which is the gating mechanism that flexibly controls the memory. In other words, it decides how much information should be forgotten. For example, it can update the memory without affecting the past abstraction by letting alpha sub t go to 0, and it can clear the entire memory by letting alpha sub t go to 1. And if you look at the first equation up here, the S sub t on the right-hand side of the equation, that's like the surprise thing, right? That's the surprise factor. The M sub t minus 1 is my memory at time step t minus 1. And if you look at alpha, if alpha is 0, it's going to remember it, right? It's going to multiply by 1. Whereas if alpha is 1, 1 minus 1 is 0, so it's going to forget its memory. It's going to clear the memory. Memory has nothing to do with what's going on right now. It's not going to care about this long-term memory. Then they go on and they talk about the memory architecture beyond the scope of this paper. Really, really interesting stuff and everything. But then they go on to retrieving a memory, and that's an important thing as well. It's not just important to be able to, get surprised, remember things, forget things, but how do you get a memory back? In the above, we discuss how one can design and train a long-term memory module that learns to memorize at test time. A key remaining question is, how can one retrieve information from that memory? We simply use the forward pass without a wait update. In other words, words, inference, to retrieve a memory corresponding to a query. In other words, they basically treat it like a classic transformer. They just pass it through, don't update the weights, and take the result that comes out. That is retrieval of the memory, of long-term memory, plus the persistent task-related memory, plus the short-term memory that's very context aware of what's going on right now. Again, a very good analogy is a human being, the way we remember things based on all of these different types of memory. Then they discuss how to parallelize the long-term memory training. This is important as an engineering thing. It's important to be able to do this efficiently. Not so important theoretically right now, but it is important because this means that this can actually be put into products and we can use it, as opposed to just being a really interesting lab experiment that would never see the light of day. Again, Google is a company that wants to productize these things, so of course they want to be able to see how, if you had 1,000 GPUs, could you put this across 1,000 GPUs? So anyway, they show how you can parallelize this long-term memory training, which is very, very critical to being able to use this in a real product. And if you want the really geeky details, basically they use matrix multipliers and summations. That's how they do it, which is more or less how attention mechanisms work already, but they figured out a way to just use matmulls and summations. And just one more time talking about the variables alpha, theta, and eta here, they say instead of making them input dependent, in other words, a function of a token X, we make them functions of their chunk. And that allows them to be parallelized as well. Because if you don't do that, they're going to depend on what just happened, which puts us in a linear situation again as well, right? If every time step you have to look at eta or something, or theta, you have to say, well, what just happened and how am I going to update things? That means you have to go back and do it all linearly, and that's going to break the parallelization. So what you do is you break these apart and you modify them by chunk. So you get a blob of data or something that you're going to act on, and you just have one alpha, theta, and eta for that blob of stuff. And then you might change that for another blob. But that allows you to vary these variables, which is very important. It's the memory weighting, it's the forgetfulness decay rate, all of that kind of stuff needs to be modified, but you can't do it on a per instance basis. You have to get chunks of data, leave it fixed for that chunk, and then adjust it after that. So that's how you can parallelize for that. And then finally, yay, we get some pictures here that might prove useful. So we get the first of the three titans, which is memory as context, or MAC architecture. So you can see we've got our three things. We've got our task-related persistent memory. Notice this says this is fixed. This is the thing that you spent all that money training. So that's going to just stay the way it is right now. Then you've got your core memory, which is your short-term memory. And then you've got your contextual memory, which is your long-term memory. So in this case, memory as context, what you do is you take, this is what's incoming. This is the thing that's happening right now. You then prepend onto this your task-related specific memory. You also then prepend, you go through a retrieval process. You go like, well, what out of my long-term memory is relevant to what's happening right now? You retrieve that, sort of like a retrieval augmented generation, but it's out of your memory rather than out of a handbook or something. You then get that information and you prepend it to your core memory as well. And then you attach your core memory. Then you do the classic transformer thing. You go like, well, okay, here's my attention layer. What do I need to look at? What do I need to pay attention for? All of this stuff, the long-term memory, my skill memory, and what's happening right now. And then you pass that through a nonlinear activation function and you produce some sort of output, a guess of what's going to happen. But then very, very critically, at the same time, you actually pass some of this attention layer up to the update layer for your neural memory, which allows your long-term memory to learn. It's like, oh, do I need to learn from this? Oh yeah, okay, I do. And then I guess what you're doing is you're actually updating the memory and passing that through the nonlinear activation function at the same time. That's interesting. I would think that that would be an asynchronous step, but it looks like it actually updates this at the same time that it passes this through, and it does the nonlinear activation function at the same time using the updated neural memory, not the old one. So interesting aspect of this. And so your core memory really doesn't learn anything. It's not learning anything new. It's just increasing its context because it's generating the next token. And of course, your persistent memory doesn't learn anything either. But what's really learning here is your contextual memory is able to update itself while this is going on, which means it's learning as you're doing this. And of course, as they say with Mac, this is a context. The long-term memory adds a context to what's going on right now. So with that previous figure in mind, let's turn now to memory as a gate, or MAG architecture. This architecture similarly has three branches. So it's got the core memory, the contextual memory, and persistent memory. It, however, incorporates only persistent memory into the context and combines the memory with the core branch using a gating mechanism. And interestingly enough, at test time, the behavior is the same as the previous one. It just doesn't learn anything, basically. So here you've got your core memory. You take your task-related memory. Again, if it's driving or something, it's like, how do I drive? You prepend that information and you go like, well, now what's going on? I'm in this, then I need to make a left turn or something like that, right? So you take those two things and then you provide attention. You go through your attention layer, all of that stuff. And then you actually use neural memory to go like, well, do I remember a similar situation? Or have I been here before? Or something along those lines. You then can use that as a gating function to say like, hey, maybe I don't need to be paying attention to the things I thought I needed to be paying attention to. So it operates more or less the same as what we saw because it's using the neural memory and it's doing a nonlinear activation function. What we're not getting, however, is the long-term memory being fed into the core memory, the current working memory that's going on right now. And we're not getting updates to the neural memory. So it's acting as a gate, right? It's like open shut kind of gate sort of situation, but it's not learning anything in this context and it's not feeding into the way the core memory is thinking about. It's just acting more or less as a gatekeeper. And then finally, we have memory as a layer or MAL architecture. And this is much more similar to the way that traditional transformer architecture works. You take your sequence, you push in your skill-based memory. We've already seen this. You prepend it to it. Then you pass that through your long-term memory. So you're like, hey, anything you want to add to this, right? Do you remember something? Anything you want to change? Anything that you think is important that's not in the current context? Then you pass that through attention. The attention layer looks at all of that stuff. There would still be a nonlinear activation function going on here, but it's a traditional one. It doesn't actually intersect the neural memory with the attention layer. It runs the neural memory first in series before it gets to attention. And so basically this is a way of having a memory of stuff that happened before, right? Let's say it was like a really long conversation you've had with some evolution of ChatGPT 5.0 or something like that has this built in. What would happen is instead of forgetting the stuff that you had talked about before, it could remember for years what you guys talked about in this little box of memory that it has. Now, it's not going to be a perfect memory like you expect computers to have because it's going to forget things using that forgetting mechanism, but it will remember the most pertinent things. And if you ask it to write you something, that's the persistent memory. That's like, how do I write, right? Basic writing skills. You pass it in your prompt right now. Write me an essay about how large language models remember things, right? That's your prompt. So it prepends all that stuff. But then it goes like, well, John and I have had a lot of chats about these things, and we've talked about the existential nature of memory and time and blah, blah, blah. And it adds that stuff into the context of everything, what it thinks is relevant, and then passes it to the attention layer that then goes like, oh, okay, I've got all of this information. What am I going to output next? So from a this is interesting perspective, the memory as context or MAC architecture is definitely the most interesting because here you're retrieving all of these elements, both the thing that's happening right now, your skill-based memory, and also your long-term memory. You're using all of that at the same time. You're retrieving long-term memory based on what's happening right now. You're saying, what's the important stuff that's going on? Then you're passing that through an attention layer to like, wait, what do I need to pay attention to? Then you're updating your neural memory and you're using that in a non-linear way. In fact, they say that they use sigmoid linear units, which is a very, very cool blending of sigmoids and ReLUs and things like that. But they use a non-linear activation function to, blend these two things together to create the output. So this MAC architecture is by far the most interesting because there's the most stuff going on. It's the most different from traditional transformers, and it's where the neural memory can actually become surprised, update itself, forget other things. That's where it's the most active, and so it's the most interesting. So then they go through experimental setup and stuff, and they go to results, and they win. You can see they have the top curves here, So trust me, you can look at this in more detail. Of course, I will leave a link to the archive paper in the description, but you can look at this in more detail. But basically, they're doing really, really well at large context stuff. And so finally, that brings us to the conclusion. In this paper, we present a neural long-term memory that, as a meta in-context learner, remember it's learning in context, doing it at test time, at inference time, learns to memorize at test time. The neural memory module is a recurrent model in nature and is adaptively memorizing tokens that are most surprising, right? Again, that gradient between expectation and what actually happens, or are close to surprising tokens in time. Comparing to modern recurrent models, it has more expressive memory update and storage storing mechanism. Using this memory, we present Titan's architectures and its 3 variants in which we suggest to incorporate the memory module as 1, context, 2, gating, and 3, layer. Our experimental evaluation on diverse tasks validates that Titans are more effective than transformers and recent modern linear recurrent models specifically for long contexts. That is, Titans can scale to larger than 2 million tokens context window size with better accuracy than baselines. All right, so that's how you use surprise to create a meta model that can learn things in long-term memory and also forget things just as importantly. It's really, really fascinating stuff. Let me know in the comments what you think about all of this. And of course, please subscribe, because not only does it help me, but also you will be able to check out the Sakana AI paper I will review fairly shortly. And in the meantime, I will see you in the next video. Bye-bye.